I hope you can see my screen.
Yes, sir.
Okay. So today we are going to cover this topic called time and space complexity. You might have come across this term like while you were studying maybe DSA or even data science. A bit about my background. I am a civil engineer by education, and since then I've been in data science. Currently, I am a lead data scientist at this company called Skook, and I also teach data science at various places, including Cordera. And feel free to connect with me on LinkedIn. Uh, Coming to what is complexity and why do we need to analyze it? Okay. Uh, Feel free to stop me in between if you have any questions. Okay. And if you have any thoughts, just let me know. Um, why analyze complexity? It helps in optimizing code efficiency, crucial for code interviews, and it has a lot of real world applications. Has anyone heard of these applications? Search algorithms, database indexing, feed ranking, financial transaction post processing, data analytics, any one of these? Okay. Um, so like in a nutshell, like complexity, time and space both. If you are able to calculate the time and space complexity of your code, then only you can even hope to make it better. And that is where the first point comes in. That's the most important thing. Like it helps you optimize the code. Now, what is time complexity? Okay. Would anyone like to tell me what is time complexity? Have you ever studied it? Have you ever come across this term before? Yeah, hi Pradeep. You are saying something.
Hello, sir.
Yeah.
Hello.
Yes, hi Vaishnavi.
Yes, sir. It is a description of how much computer time is required to run algorithm.
Okay. So this is
Yeah.
a very common misconception that time complexity is actually the amount of time needed to run a code. But let's talk about that. Okay, so I'll share my uh, this thing. Okay. Are you able to see my notepad?
Yes, sir.
Okay. So there are now two things. The first thing is the amount of time taken to run a code. Let's take a very simple code. I hope all of you guys are familiar with Python since you are in a data science course. So let's take a simple function, def, let's say a function that print numbers, and it takes a number, let's say n, and it just prints every integer from 1 till n. So the code will be like this for I in range 1 to n or n plus 1, whatever, and print I. Okay. Uh, there are two things that can be said about this code. One is the amount of time needed to run this. And there's another thing called time complexity. Okay. These are two separate things. In terms of amount of time needed to run it, it can be anywhere from 0. Maybe 0.1 milliseconds to 0.1 milliseconds. It can be anywhere in this range, depending on n, of course. If you keep n equals to maybe 10 billion, then it might take a lot longer than that. It might even take a few days to run the code. Okay. But the time complexity still stays the same. The time needed to run varies with the input, but the time complexity is we denote it in this form, O of n. Okay. So no matter what n is, time complexity is always O of n, even though the amount of time needed to run changes with n. Okay. This is the first thing that you should know about time complexity. Any questions till now? Okay. Now coming to the notation part. Okay, let me share back the slides. Yeah, I hope the slides are visible. The time complexity measures how runtime grows with the input size n. Uh, the big O notation is the most common way of measuring it. It describes the upper bound of runtime. And let's see. Okay, let's come to this introduction first, and then we'll dive deeper into all the topics. Coming to space complexity, uh, it measures how the memory usage grows with the input size n. Just like time complexity was how the runtime grows with the size n, space complexity is how the memory usage grows. Okay, and there are two factors in it. One is the auxiliary space, and one is the input space. So in any function that you are running, you will give some input, and that input will take up some space, and the function by itself will use up some extra memory that we can call it as auxiliary space. So that also you need to take into account. Uh, Anyone is saying something? Okay. Um, Example is recursion versus iteration in Fibonacci sequence. We'll see some examples later. But coming to the notation part, there are three kinds of notation that you will usually see. One is a big O, one is a big theta, and one is a big omega. For any algorithm to run, you can represent the time complexity in these three ways. Big O represents the worst case performance. Okay. For example, let's take any sorting algorithm. You might have studied some sorting algorithms like merge sort or quick sort, right? Or you might have studied some search algorithms like binary search, linear search, right? So all of these algorithms can have different worst case, best case, and average case performance. So uh, big O denotes the worst case scenario. Okay, we'll look at how can these three be different in different cases. Big theta is the average performance. Okay, so in a typical case, what would be the time taken to run the code in terms of n? Okay, and you denote it using this theta notation. Coming to omega, omega is the denotes the best case performance. So maybe if let's say you are doing a search algorithm. So let's say you have a list of numbers and you want to search a particular number in it, whether it's present or not. The worst case would be if you're starting from the beginning, the worst case would be that you either find it at the end or you don't find it at all. You have to go through all the elements of the list in both cases. That is the worst case. The best case would be that you find it uh, in the first element itself. That is the best case. That will take the least amount of time. And the average case might be that you find it in the middle of the list. Okay. Is this clear? What is the difference between big O, big theta, and big omega? Anyone has any questions, you can raise your hands. Okay. I'll assume that no one has any questions. Okay. Now coming to usually in your interviews, you'll always be asked the big O complexity. That's the worst case complexity. Okay, because usually that is something that is the only thing that we care about. How much time will it take in the worst case? Okay, so that's why we'll from now on we'll only focus on big O complexity. And this is how the graph looks like for uh, like different complexities. Let me share the notepad again. Uh, you might have studied something similar in like maybe in your school maths, like plotting graphs of different functions. So if you remember, y equals x might have looked like this. This would be the line. Okay, it is a 45-degree line going through this origin. Y equals x square would have looked like this. This would be an upward facing parabola going through the origin. Y equals to x cube might have looked like this. It would be something like this going again through the origin. and y equals maybe log x might have looked like this, where it starts from negative infinity and goes like this, and it is x is never allowed to be negative. Some other functions would be exponential of x, so it can be either e to the power x or any number to the power of x, where it would look something like this. And so yeah, similarly, you might have studied a lot of functions back in school or college, and these will come in really handy for us today while seeing like what does the time complexity graphs look like. So the like I'll list down some most commonly used or most commonly seen time complexities. O of 1, O of n, or even before that it will be O of log n, O of n, O of n log n, O of n square, O of n cube. It can even be like higher powers, or it can go up to O of n factorial, or O of some k to the power of n. K can be anything. It can be e, or it can be 2, or it can be 10. Okay, so these are different complexities, and you can plot these just like you have plotted these curves. I will go back to the slides. So if you see O of 1, what does that look like? That is the lightest green color. You'll see this here in the bottom. You'll see that's a flat line. It is difficult to see, but it is there. It's a flat line, and that does not have any slope. That's a flat line. So um, please don't annotate the screen. Whoever is doing it. Second is O of log n. That is a bit worse or a bit higher than O of 1, and that is almost flat. If you zoom it in, you will see some height of it. O of n will be a straight line going to the origin. That is this whatever color this is, probably maple green or something. That is this one. N log n is this white or beige, whatever this color is called. This line that is, even though it looks like a straight line, but it is curving upwards slowly. N square is the parabola. That is this one. Is my mouse pointer visible?
Yes, sir.
Okay. And 2 to the power of n, that grows even faster than n square, because that is exponential. And next we have n factorial, that grows even faster than 2 to the power of n. Okay. These are like very commonly found time complexities that you will face whenever you're solving any problem. Coming to an example, who all have studied this algorithm called bubble sort? Who all have not studied it ever? Can you give me a general idea? Like, have you studied any sorting algorithm ever? Anyone?
Yes, sir, we have.
Okay. So assuming that you know in general what bubble sort is, you don't need to be able to write the code right now because the code is already here. But you should have a general idea. I'll just explain a general idea anyways. So assuming, let's say you have a list of numbers like this. Let's say 8, 1, 2, 3, 7, 5. Okay, this is the list of numbers that you have, and you want to sort this list in an ascending order. The way that bubble sort would work is it would first check the first pair of numbers, 8 and 1. And whichever is bigger, it would just shift it towards the right. Okay, so it would swap this and it will become 1, 8, and the rest of them will stay like this. Then it would check this pair. So then it is checking 8 and 2. It will again swap it. So then it will become 1, 2, 8. And so on. It will keep doing this with every consecutive pair until it reaches the end. And at the end, what will happen is the final list will become like this: 1, 2, 3, 7, 5, 8. So 8 actually floats at the end. Okay. So the largest of the elements moves towards the end in the first iteration. Now you will do the second iteration where you will again compare the first two, then the second and third, then third and fourth, and this is still okay. Then fourth and fifth, this way here we'll have to swap. So we'll swap 5 and 7. So it will be 5, 7, and 8. And that's it, because the last element is already fixed. And then we'll keep doing these iterations until there are no swaps happening. As soon as there are no swaps happening, we end the algorithm. That means that the array has been sorted. So you can see this condition. If not swapped, then break. That means if no swaps happened, then you're breaking the algorithm. Now we can take this example and try to calculate its time complexity. Okay. The way to calculate time complexity is basically just calculate the number of operations happening and relate it to the input size. Okay. Here the input is the array, this ARR, and it will have a particular size. Let's say the length of ARR is equal to n maybe. Okay. So let's take a number. Instead of n, let's take 10. Now I want to calculate whatever code lines I have written. I want to calculate how many operations does it take to run that code. Okay, so this is one operation. So I'll use another color. One operation. Okay, this for loop, anything inside this for loop will run in the worst case n number of times. Okay, swapped equals to false, one operation. This for loop will run in the worst case how many times? N minus I minus 1 times. Okay, this condition checking, one operation. This swapping, one operation. This assignment, one operation. Checking, one operation. This breaking, one operation. We are taking the worst case. Okay. Now, if we consider inside whatever was inside this loop would have been executed n minus I minus 1 times. Okay. So how many total operations are there? There are 3 operations happening inside this loop: 1, 2, and 3. So the final number of operations will be 3 times n minus I minus 1. We don't know I, but we'll just take the worst case scenario. What is the worst case scenario for this term? When this term will be the highest? This will probably be the highest when I is minimum, if that makes sense. Does that make sense? Any questions? Worst case, I is minimum. So I'll just, minimum I can be 0. Okay. So I'll just consider it 0, and the total number of operations will be 3 times n minus 1. And this whole thing is happening inside as another loop, which happens in the worst case n times. So what are the total number of operations happening? This is 1 plus this loop. This loop was 3n minus 1, and two extra operations plus 2. This whole thing is happening n times. Okay, and then this one extra operation. So I'll just add one here. So what is the total number of operations here? I'll write it over here. The total number of operations becomes 1 plus n times 1 plus 3 n minus 1 plus 2. And this is just approximating. Okay, we might have missed 1 or 2 operations here and there, but that is okay. The only thing that matters here is we are taking the order of the degree of the polynomial correct. Okay. So if we calculate net, it will be 1 plus n. 1 plus 2 is 3. You can take 3 outside. So this is 3. And here it will be n only n left inside. So net it will be 3n square plus 1. Okay. Now, whatever expression you get here, just take the highest degree of the polynomial. Okay, that is 2, right? N square. This whole algorithm becomes O of n square. Okay. Anyone has any questions in this? Would you like me to explain anything again? let's go one by one. I'm seeing people are muting. Nishant, you want to say
So, can you please explain the previous part again?
which one?
The one that you just explained, sir. I missed it because of my network.
Okay, I'll do that. Siddhant, is there a question?
Sir, can you explain without taking a single operation count? Like only take the n
Yeah,
and n.
yeah,
Don't calculate the one each one
yeah.
expression.
You can do that. And it'll again lead you to the same answer. Okay, you can do that. So the easiest and the fastest way to do it is just look at the loops. Okay, how many loops do you have? Or if it is a recursive algorithm, look at the recursion stack. Okay. I took into account all the operations because that is the right way to do it. That is the longer way to do it. But a shortcut is to just look at the anything that has anything to do with the n, that is the input size. Okay. So basically, if I wanted to do it like a bit faster, I would just look at these two loops. And in the worst case, the first loop runs n times, and the second loop runs something n like a linear form of n, okay, n plus something k times. And that has a n square term here, that is the highest degree term, and that gives you the complexity of O of n square. Okay.
Thank you, sir.
Yeah. Someone, Nishant asked the question like, Nishant, is this clear now?
Yes, sir.
Okay. Okay. So I'm assuming there are no other questions. Let's move ahead. I hope you guys understand now how to calculate the time complexity. The same thing can be done with space complexity as well. Just calculate how much space you are taking up while running the algorithm. Okay. So for example, I'll erase all this. Okay. I'll erase this. This is enough. So if you want to see how much space is my algorithm taking up, the way that we'll do it is we'll just see what all variables are we creating. This is one variable n. What else? We are creating another variable swapped, two variables. Then that's it, right? We are not creating anything else. So for no matter what the input size is, you are just creating two variables. Okay, two variables, and even you can look at the size of these individual variables. That is, n if it is an integer, it might be 8 bytes, and swapped is a boolean. It might be even like 1 bit. Okay, so just confirm whatever sizes it is, and it is a constant size. Doesn't matter what input size was. Okay, no matter what the input size was, you'll always take this much space to run your algorithm, and this is a constant space, and that you denote it as O of 1. Okay, so in a nutshell, the final result, if you want to say, the time complexity is O of n square, and the space complexity of this algorithm is O of 1. Any questions on this?
No, sir.
Okay, let's move ahead. Okay. Okay. Coming to the worst case, average case, and best case. In the worst case, we just saw that it is O of n square. Average case, this is the omega thing. Sorry, not the omega thing, the theta thing. If you calculate in the theta terms, it will be again n square, because if you just see what all cases can be there, you see different lists of numbers which are already sorted to a different extent. So maybe like one list can be that it is sorted in a descending order. So for example, let's take one list that is like this: 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. This is the input list and we want to sort it in the ascending order. This will take the maximum effort. This is the worst case actually for us. Okay. This is again O of n square. But if you take the average case, maybe half of the list is already sorted. Okay, so maybe 1, 2, 3, 4, 5. Half list is already sorted, and the rest of the half list you want to sort. So the rest of the list can be something like 10, 9, 8, 7, 6. If this is the list, that is the average case. Average case means the theta n square. This will still take n square operations. Okay. And the best case will be the list is already sorted. So it is this list that you are giving as input. And since we are stopping whenever no swap has been made, it will just stop after iterating through it once. And it will just stop it. And since you're just iterating through it once, it will be off n. If that makes sense. You are just doing n operations. Any questions in this? Okay. Here are some examples of different kinds of time complexities. Okay. Constant time. This is a function. This is written in C++. I hope you guys are familiar with the syntax. Even if not, it's fairly simple. Just like in Python, like you can assume that this is def and this is a function name, and these are the input parameters. That is, one input is a list, that is array, and one is the index. Okay, these are two inputs, maybe A and I, something like this you can assume. And you're just returning the ith value of the array. Okay. And since like accessing ith element of array, that is a constant time operation. Okay, hence it is the time complexity is O of 1. What about the space complexity? Anyone? What is space complexity of this algorithm to get the ith element of the array? No one? Okay, it is also O of 1 because you're not creating anything extra. Okay. Next. This is logarithmic time. Basically, this is O of log n. This one. The way to understand this is basically this is binary search, and the way who all know what is binary search? How does it work? What is binary search?
It
Sir, finding the
searches
middle
the
value.
it searches the element even either first half or the last.
Okay, yeah. So basically the input has to be sorted. Okay, that is the assumption. Assumption here is input list is already sorted. So what will happen is, let's say if this is your list, 1, 2, 3, 4, 5, 7, and you want to find, let's say 4, or maybe you want to find 5. Okay, this is our target. So what it will do is it will see the first element, the last element, and the middle element. Middle element, maybe let's say is 3. Now, since 5 is greater than 3 and less than 7, you know that it will be in this second, like right end. Okay. And then you again break it down into half, and then again search in the left or the right one. And you keep splitting it into half and half and half at every step, and until you reach the target or you cannot find the target. Okay, that is these are two possibilities. So either the target is there and you reach the target by cutting the list into half and half and half every time, or there is no, like, the element doesn't exist in the list. Okay, this is how binary search happens. And since at every step you are cutting the number of operations into half, so basically if the list was let's say 128 elements long, 120 elements, then you would cut it into half into 64, then you would cut it to 32, then 16, then 8, then 4, then 2, and then 1. Either you end at 1 or you say that you did not find the element. So how many steps did it take? This is 1, okay, 2, 3, 4, 5, 6, 7 steps. Now, if you take a bigger list, maybe let's say you take a list that has 1024 elements. We'll see why I'm taking like such specific numbers. But if you split that into half, you get 512. Then you split that into half, then you get 256. Then you split that into half, then you get 128. Then the same numbers will happen here also. Okay, 128, 64, 32, and so on. So after this, you take 7 steps plus 1 plus 1 again and plus 1 again. That is total 10 steps. So basically, if you just notice the pattern here, the pattern is that 128 is nothing but 2 to the power of 7. 1024 is nothing but 2 to the power of 10. Okay. So whatever is the power, that many steps it is taking for us to do binary search. Okay. And so basically, if the list size is n, if you want whatever is the list size, okay, let's say the size is equals to n, or if you want to take it 2 to the power of k, then how do you find out k? Because k is your time complexity. K is nothing but log of n. Okay. If you just take yes, Omkar. You want to say something, Omkar? Okay. So this is our k and this is the number of steps. Okay. Number of steps taken. And this is our time complexity. So this becomes O of log n. Okay. Any questions in this logarithmic time complexity? So the pattern to recognize here is whenever you have an algorithm where this cutting into half is happening at every step, not even cutting into half, maybe cutting into a certain size at every step, then think of log. Okay. It can even be cutting into 3 parts at every step. Okay. Then again, it will be something like log, the base will be different, but it will be log of n. Okay. So whenever you have an algorithm that you want to analyze and certain part of the algorithm is doing this, then that is what you should take that as a time complexity. Okay. I hope there are no questions. Okay. Moving on to linear time. Linear time is nothing but O of n. So basically, it is linear in input size. Okay. So if the input size is n, you can take how many operations to complete the task? You can take something n plus something k, some constant number, or maybe a n plus k, where a and k are constants. Okay. But the degree of the whole polynomial should be n. Okay. Any questions here? Okay. Next is linear arithmetic time. That is a combination of linear and logarithmic. If you have studied this sorting algorithm called merge sort, you will find this, and it takes n log n amount of time to solve. Okay. If you want to like go a bit deeper into this, like how is this n log n, then you can simply see that the way that this happens is if you just read the algorithm itself, you first divide the list into two parts and keep dividing into two parts until it's just one element, and then you join the two parts of the list while sorting it. Okay. So basically, dividing into half. Okay, these are two things that happen. Divide into half and then merge two halves. Okay, these are two steps that is happening in this algorithm. In dividing into half, we already saw what's the complexity here, log n. Okay, merging two half. So how much? So the logic here is if you have two halves that are individually sorted, how much time will it take to join these two halves such that the resultant is also sorted? Okay, so for example, if you have two lists like 1, 4, 7, this is 1, and the second list is maybe 2, 5, 10. Okay, if you want to join these two lists such that the resultant list is also sorted, what will happen is you will start like two pointers, right? One pointer here, one pointer here, and you will see, you will compare these two. Okay, and you will, whatever is lower, you'll put that here, and whenever you put something here, you just move that pointer towards the right. Now it is 4 and 2. Okay, you just compare whichever is lower. 2 is lower, so you put 2 here and you move this ahead. Okay, now the pointers have 4 and 5. You put the lower one, 4, and move it ahead. Now you have 5 and 7. 5 is lower, move that ahead. Now you have 7 and 10. 7 is lower. There's nothing after 7, so you end this here, and then you put the remaining 10, and there's nothing after 10, then you end it here. So you had to go through the sum of these elements number of times to do this. So if this half has, let's say, n number of elements, and this half is also n number of elements, you took O of n number of steps, or basically you took 2n number of steps, and that is actually equal to O of n. Okay, so basically log n into n. Okay, because you're dividing at each step as well. Any questions here? Am I going too fast, too slow? Any thoughts?
No, sir.
Okay. So this is our n log n time complexity. Let's move on. Quadratic time, this we already saw in bubble sort. There you have two lists like this, one of like nested lists. This runs n times. This also runs so n times in the worst case. And inside this, there is an O of 1 time complexity operation. This is this the inner operations happens in constant time. So the net complexity becomes n square. Okay. And here, since we are not even using any extra space as such, apart from this I and j, right? So I and j will take up some space, but this is a constant amount of space. So the space complexity will be O of 1. Then time complexity is O of n square. One more important point to know here is whenever you have an algorithm which has time complexity maybe n of n square and space complexity as O of 1 or any other complexity, usually if you want to optimize this algorithm, usually, okay, this is not a rule, okay? Usually when you optimize it, you might be able to optimize it to O of n log n. But as a trade-off, space complexity might increase to O of n. Okay, that might happen. You will actually see this in a lot of problems that you will solve later. When you decrease the time complexity, you have to increase the space complexity. That is a trade-off. Okay, but this does not happen every time. But usually it will happen if the initial algorithm is not too bad.
Sir,
Okay, if the initial algorithm is just the worst algorithm that you can use, then this might not happen. You can actually save up on time complexity without increasing space complexity. But if you have a decent enough initial algorithm, if you optimize it further, you have to do a trade-off with something else. Exponential time, you might have solved this question to print the Fibonacci series. And since this growth, the tree
Sir,
is going
hello.
exponential. Yeah, hi Pradeep.
Is it Java programs?
This is C++, what you're seeing here. But
C++.
but
Okay.
the same concept applies to any other language, including Python, Java, Golang, whatever language you're doing. This
Python.
concept is language independent. Okay.
Okay, sir.
In the Fibonacci series, usually what happens is, let's say you want to find 100 terms of the series. So it'll keep calling n minus 1, n minus 2 over it. So basically, if you give n equals to 100, you'll be calling Fibonacci of 99 plus Fibonacci of 98. That will be equal to Fibonacci of 100. Fibonacci of 99 will call Fibonacci of 98 plus 97. 98 will call Fibonacci of 97 plus 96, and so on. This keeps expanding exponentially. That's why it is exponential time complexity of 2 to the power of n. Okay. Basically 100 calls 99, 98. 99 calls 98, 97. 98 calls 97, 96. This calls two others, this calls two others, two others, two others, and this keeps going as a exponential of 2. Okay, this is 2, this is 4, this will be 8, and this then 16, and so on. This is power of 2. Next, I'll try to move a bit quicker because we are short on time. This is factorial time. This is like printing all the permutations of a given string or a given list. And this is a backtracking algorithm. If you don't know this, don't worry about it. You'll, like, in 90% of the use cases, you'll not encounter this. Okay. But just remember that in permutation related algorithms, you might find a factorial time complexity O of n factorial. So if you have a string that looks like 1, 2, 3, 4, if you want to know how many permutations can there be, it is usually 4 factorial. Okay. Because the first place can have 4 numbers, second place can have 3, then 2, then 1. And this is nothing but 4 factorial, and that is how much? 24. Okay. Yeah, these are some common complexity as we went through already. Accessing array element, looping through an array is n. Bubble sort and most other sorts apart from merge sort is n square. Binary search is log n. Merge sort is n log n. Okay, some practice problems. This is the summary of what we just went through already. Counting operations. Okay, this is very important. Counting operations inside loops. Okay, not even loops, like counting all the operations will really help you out in calculating the time complexity, but you can take some shortcuts and do it only for loops because they are usually the most operation intensive tasks. Or even recursion depths. If you have a recursive algorithm, then there might be no loop, but there might be a recursion tree. So look at that. And you want to evaluate the overall growth of operations with respect to n. Okay. Similarly, space complexity, measuring the memory usage, just look at how much memory you're creating separately, including all the variables that you are creating. Variables, data structures, and the recursion stack. Okay. Now, these are some problems for you. I want you to solve this. Can you tell me? So here, just for ease, I have written the same algorithm in Python as well as C++. Okay, this is Python. Whoever is more comfortable in Python, look at this. Whoever is more comfortable in either C, C++ or Java, you can look at this. Okay, the second one. These both are the same algorithms. Tell me the time and space complexities. Let's see who can tell me first. This is a linear search. You want to find whether the target element is present in the list or not.
Time complexities big O of n. Space complexities big O of 1.
Perfect. Okay. Who was this?
Lavanya here, sir.
Lavanya. Okay. Great job, Lavanya. Time complexity of n because you are doing n operations, and space complexity is of 1 because you are not really creating any variables as such. Okay. I hope everyone is clear on this. We'll move ahead. Okay. O of n, O of 1. Okay. Next, this is binary search. The same algorithm again, one in Python, one in C++. Look at it, whichever language you're more comfortable in, and tell me the time and space complexities. This is
Time
what yeah,
complexity big O of log n. Space complexity big O of 1.
okay, that's correct. And anyone has any questions on this? How did Lavanya solve it? I hope this is clear. Okay, so since we are dividing the list into half every single time where we are doing this, basically we're taking the mid element and then checking only around the mid element, like mid and left and mid and right, and we are doing this repeatedly. That's why it is taking us log n of operations. Next. This is bubble sort. We already discussed this. Let's see if you remember this. What's the time and space complexity?
Because of nested loop big O of n square. And big O of 1 is space complexity.
Perfect. Okay, so there is a nested loop n inside n. Okay, so this will contribute one n, this will contribute another n, and the net will become n square. And since we are not creating any more such elements which relate to the input size, that's why O of 1 is the space complexity. Next. The Fibonacci series, we are printing the Fibonacci series. No, sorry, we are generating the nth term of the Fibonacci series. So here there are no loops, but still there will be some time complexity because it's a recursive algorithm. You have to look at the recursion stack. How many operations are happening behind the scenes? You need more time.
Because the recursion is divided into n is
Yeah.
divided into recursive functions, so it 2 raised to
Perfect. And space?
uh, space is big O of n
N?
1, I think. No, sir, I can't able to
It is
calculate.
N. It is
Oh.
N, okay? Because of the recursion stack. Make sense?
Okay, sir.
The depth is N. These are two algorithms. This is the recursive algorithm that we just saw, and you can ignore this. Okay, this is another algorithm where you want to find the maximum number in the array or the list. Okay, these are the same codes, just left one is in Python, right one is in C++. Okay, so what is the time and space complexity?
Big O of n is time complexity and big O of 1 it's space complexity.
Perfect. Okay, same logic as earlier. Next algorithm is checking for duplicates. This is a brute force algorithm. You want to see whether there is any duplicate present in the array or not. Okay. It's again very simple. The same logic as earlier.
Big O of n square time complexity and big O of 1
One.
space
Right?
complexity.
Perfect. This is the same problem, that is finding duplicates, but this is a better way to do it. This is an optimized way to do it. Can you find out the time complexity of this? This might be a bit tricky. One. I'll help you out. So if you see, you're creating a set here. Okay. Similarly, here also you're creating an unordered set. And then you are doing a loop. So obviously the time complexity will be O of n because there's a single loop and there are, in the worst case, n operations happening. Okay. And you are adding the number in this set, scene.add num or scene.insert num. And that's where you are actually creating in the worst case, n sized array or a list. Okay, so space complexity is again O of n. Does that make sense? Okay, I'll assume there are no questions.
One question, sir. If
Yeah,
uh, yeah, if we having a list 1, 2, 3, again 1. In this
yeah,
case, uh, the for loop will be executed 1, 1 in scene no, so it will add 1,
yeah.
2, 3. till 3 it repeated the same loop.
Yeah.
When one is comes, then it return from function.
Yeah.
Take that after 1 we having 4, like 1 2 3 1 and 4. And what happens with 4?
You're saying 1, 2, 3, 4.
1 2 3 1
Okay.
and after that 4.
Yeah.
So
So
in
what
that
happens in the algorithm? So basically, it will check whether one is there in scene. It is not, so it will add one. So let's take this is the set. Okay, it will add one. Then it will go with two. It will check if two is in scene. No, it will add two. Then it will check for three. If three is in scene, no, it will add three. And it will go to one, and if it will check whether one is there in scene. Yes, it is there, right? So it will return true. That's where the algorithm will end. So it will just return true that there are duplicates in the array.
okay.
Okay. So this is the summary. This is we already gone through this. This is one problem that I want you to try as a homework. This is a two-sum problem. You will find this very easily on either LeetCode or HackerRank. Just Google it, you'll find it. This is the problem where you have a list of numbers and you have a target. You want to find two numbers in the list which sum up to the target. Okay, that is the problem. You have to find two numbers in the list which add up to the target. And there are different algorithms to do it. There will be a very brute force algorithm that will be very high time complexity, and there will be some optimized version as well. So try to find the time complexity of each of the algorithms that you can come up with. Okay, this is your homework, and we'll probably meet again in another 2 weeks. So probably around 15th or 16th, and we'll see like whatever topic we are covering, but we can also discuss this homework if you have done it. Okay, so this is the answer for it if you want to see it, but try to do it yourself. Okay, that's it for now. And any questions? Any last questions? Okay, I hope there are no questions. If you have any questions, feel free to contact me, or feel free to contact your instructors at Cordnera, and feel free to connect with me on LinkedIn if you want to ask me something. Okay, my name is Ashit Dharwal, and yeah, I'll see you guys soon in 2 weeks. Okay,
Thank you, sir.
thank you for joining, everyone.
Thank you, sir.
Have a good day. Bye.
Thank you, sir.
Thank you, sir.